Hello, welcome back to the 154 course. So today we will discuss about the quantum mechanics and also the atomic physics. I have looked on the survey, so have a lot of the topics that we in the content, but this is what I selected topics it's to be the same as the 104, so in Thai course. Okay. So we're gonna cover the evidence that we can that we had in the past that the classical mechanics, classical electrodynamics cannot be used anymore to describe the experimental result. So this including the blackbody radiation, the photoelectric effect, and the Compton effect. And then we're gonna discuss about the wave property of the particles, and then we're gonna revisit the double slit experiments. We're gonna discuss about the uncertainty principles, looking for the boundary conditions, and then we go to the hydrogen atoms from Bohr and the quantum models. Okay, let's start. So the blackbody and blackbody radiations. So the blackbody is an object of the system which absorbs all the radiation incident upon it. Okay, you can imagine that you have a volume that have a small hole here, and then if the radiation get in, it's gonna bounce inside the volume, okay, until it's reached the thermal equilibriums. Okay, so this is the what we call the black bodies. Okay. And then the black body can also radiate. So it can radiate the energies, and the radiations, it's depend on the temperature of the cavity walls only. Okay, it's not depend on the material, it's not depend on the what wave that get in, what radiation it get in. Okay, just the temperature of the wall, and that's control the radiations. Okay. An examples of the black body, it's a cavity with the hole. So this is that one. We can also use it approximation for the stars, the hot charcoals. Okay, so this is example of the black body. The wavelength distribution of the radiation from cavity was studied in 19th centuries. Okay, there are two consistent experimental findings that we're going to discuss. Okay, so the first one is this result. Okay, so from the experiment, it showed that the total power of the emitted radiation increased with the temperature, and this is what we call Stefan laws. Okay, Stefan laws say that the power equal to the sigma AE t to the power of 4. Okay. E first, E is the what we call emissivities. So it's the its ability to radiate. Okay. And then we have the sigma. So sigma is the what we call the Stefan-Boltzmann constant. So it's the value is 5.670 times 10 to the minus 8 watt per square meters per Kelvin to the power of 4. Okay. So it's called Stefan-Boltzmann's constants. Okay. This law is important. The example of using this law is the thermometers measurement using the ear thermometers. So when the temperature increase, okay, for example, it's increased 1 degree. So you have the fever. Your fever will not like 10 degree increasing. Okay, it's 1.5 degree increasing. So if you consider the the fraction of the new temperature divided by the old one, it's gonna be very, very small. It's so if you talk in Kelvin, so it's 273 plus 38 divided by 250 divided by 37, for example. So it's gonna be very small, but that will amplify in terms of the power, because power it's depend on the temperature to the power of 4. Okay, so that's why this law is very important, because if the power is it's blow up in that way, we can use the new the sensor that we have today. Technologies can also detect that precisely. Okay. So this is the first one, the Stefan laws. Okay, so just to remind that this comes from the experiments. Another one, it's called the Weir displacement laws. Okay, so the Weir displacement, so it's called displacement because we're talking about the shift. Okay, it's the shift of the peak of the wavelength. Okay, so if you're looking on the plot, you can see that if the temperature increase, so the peak it's shifting. Sorry, if the temperature decrease. Sorry, if the temperature decrease, the shift of the wavelength, it's the peak of the wavelength is shifting to the longer wavelength. Okay, it means if you have a low temperature, when it's radiate, it will radiate, but it's in the infrared regions. Okay, let's look at the formula first and we discuss the result. So the Weir displacement law say that the lambda max times the temperature equal to the one constant. So it's meters. Okay. So when T decrease, the lambda gonna be increase. Okay. And when T increase, the lambda gonna be decreased. Okay. One usual example is human body. It's radiate, but it's not radiate too. It's not radiate much. Our body temperature is like 37 degrees centigrades, right? So it's roughly 300. So you can see that if you're talking about 300 Kelvin, the radiation is gonna be in the infrared regions. Okay, so this is infrared region, and this is the UV regions, right? The UV have the higher frequency, shorter wavelength compared to the visible light. Okay, so your body radiates the infrared, so you cannot see it. Okay, because your eye is sensitive to the visible light only. So that's why if you go into the dark room, you cannot see someone if they are inside. Okay, because you use the eyes and the eyes cannot see the infrared. Okay, so yeah, this is the Weir displacement laws. Okay, so these two important results from the experiments lead with these two important results from the experiments. Physicists would like to have a model to model the Blackbody. Okay, you have the result of the experiment, you try to model it. Okay, so the models come from Rayleigh and Jeans. Okay, so they make the Rayleigh-Jeans law, where the intensity is equal to the 2 pi c kBt divided by lambda to the 4. Okay, so this derived from the classical electrodynamics and classical mechanics. Okay, we will not derive this formula in this class. Okay, but we can show the result for that. Okay. So the plot Okay, this zone is coming from the experiments, and this zone coming from the classical theory that proved from the Rayleigh and Jeans. Okay, so you can see that the result of the experiments, it's not consistent with the model. Okay, but this is the model that derived from the best knowledge we had in that time. Okay, so at the high temperature, it can predict quite precisely the behavior of the radiations. Okay. However, at the low temperature, it cannot really predict. Okay. In this formula, you can see that if the temperatures go higher and higher, the radiations from the UV region is gonna blow up to infinite, right? So when you when T is increasing a lot to infinite, the UV gonna go up to the infinite. Okay, and this should not be real. Okay, there are several objects that can have a high the high frequency, and that we don't die for the UV bombarding. Okay, so this is called the issue is called the ultraviolet catastrophe. It cannot really be described by the model, the best one that we had in that time. Okay. So we need to fix it, but to fix it, we need a new point of view. Okay, because in that time, I think that they are doing several review of what should be wrong for the classical electrodynamics, and they cannot find it. Okay, so the ad hoc assumption came from Planck. Okay, in the in the year 1900s, Planck developed a theory of the blackbody radiations. Okay, which can be agree with the experimental result at all wavelength. Okay, but he has exemptions. His assumption include that the cavity radiations came from the atomic oscillations in the cavity walls. Okay, and the energy of the oscillator have only certain discrete value. So this is the different thing. So in classical electrodynamics, you talking about the continuous spectrum of the energies, but in Planck's assumption, we don't say this is quantum yet, but this in that time, Planck assumption said that the energy is discrete. Okay, we have the discrete value of the energies. So Planck said that the energy is N, H, and F. Okay, where F is the frequency, H is a Planck constant. It's 6.26, I think, 10 to the 6.62 or 6.26, 10 to the 34, 10 to the minus 34. Let me, yeah, sometimes the 6.62, 10 to the minus 36 joule per second. Okay, so that's why we cannot really see Planck in classical electrodynamics, because it's very low value. Okay, and N is what we call the quantum states. Okay, so E have a discrete number. Okay, so you have the frequency, you can it's controlled by the frequency and it's controlled by the quantum state when you're talking about the oscillators. Okay, so this is on the figure on the right. So it shows you how Planck ideas look like. So we are talking about the oscillator that have the energy in a discrete value. Okay, so if the particles or if the system is in this state, for example, it can go up or it can go down, but it need to get the energy or it need to release the energy with exact amount. Okay, so for example, if you have the state here, So if you need to increase, you need to move it to the higher state. So to increase the energy, so it absorbs the energy, it will absorb exactly energy equal to the HF to move to the next step. Okay. But if it need to release the energy, it will release exactly the same E equal to the HF, and it's go down one quantum state. Okay, so this is the concept of Planck. So the oscillator emits or absorbs the energy when making the transition from one quantum state to the others. Okay, energy of each oscillator can have only a discrete value, and this is what we call quantized. Okay, so it have a discrete value, and then each discrete energy value corresponds to the different quantum state. Okay, so if you have the energy that corresponds to one quantum state, and you can find that if you know the frequency. So this is a Planck idea. Okay, it's different than the it's different than the classical view of the electrodynamics. So in that case, we see that the energy is continuous. Okay, so if the oscillator is remain in the same quantum state. Okay, if the oscillators remain in the same quantum state, so it will not absorb or radiates the energies. Okay. Okay, so this is what you get from Planck. Okay. So with the assumption of Planck, he re-derived the intensities. Again, we will not prove this here, but what he get is 2 pi hc square divided by lambda to the 5 e to the power hc lambda Boltzmann constant temperature, and then minus 1. So this is what the new intensity of the blackbody radiation calculated by Planck. Okay, so these intensities, okay, the importance of this intensity is that it can go back to the Rayleigh-Jeans laws when we treat the high temperature conditions. Okay, and it need to describe well the intensity of the UV regions. Okay, it's 2 conditions. So if it's talking about high temperature, larger wavelength, so this need to describe this one and this zone. Okay, and also for the UV region, this intensity should also can describe this. Okay, so if you treat that T is go up and the lambda is go up, sorry, no, I should say first we're talking about when T is lower. Yeah, when the condition Hc over lambda kBT is less than 1. Okay, it's less than 1 because we have a very long wavelength, for example. Okay, so in this case, we can expand this term equal to the 1 plus Hc lambda kBT and then minus 1. Okay, so this term can be expanded to this one. Okay, and then so it's gonna equal to the Hc divided by the lambda kbt. Okay, put it back to the I. Okay, so you're gonna get 2 pi hc squared divided by lambda to the 5 divided by hc over lambda kbt, so lambda to the power of 4, right? H is cancel, c is cancel, so you're gonna get 2 pi c did I forget something? So, okay, 2 pi c kbt divided by lambda to the 4. Okay, and so this is the Stefan sorry sorry, not Stefan, Rayleigh Jeans laws. So this is Rayleigh Jeans laws. Okay, and when we treat the lambda equal to 0 or approach 0, okay, so e to the hc divided by lambda kbt gonna approach sorry, if this 0, so it's larger than 1. Okay, so you're gonna get I, it's going to 0. Okay, so this is correct because when you have a very short wavelength, okay, when you have a very short wavelength, so it's in this zone, the intensities go down. Okay, great. So this is one example that in the past that show that the classical electrodynamics doesn't work for the to explain the experimental result. Okay. The next one is what we call the photoelectric effect. So when you shine the light to the metal, to the plate of the metals, okay, you shine the light here. Okay, it is found that the electron is knocked out and it's go. So you have the second plate, and then you apply the voltage. Okay, you can measure the currents and with respect to the change of the voltage. Okay, so situation is the light come in, somehow it's knocked the electron out. Okay, when you apply the voltage, electron gonna move, you accelerate it. Okay, it's gonna move. So when it can reach the second plate, so it's make the full circuit, so you can measure the currents. Okay, so what we see, if we're looking on one plot first, for example, low intensity, you can ignore low and high first, just looking on the behavior. Okay, so when you're shining the light with the high intensities, okay, you turn it on and then you increase the intensities, the currents will not change. Okay, you see that the current is almost the same here, right? So this is one thing that we see. Okay, so at large voltage, okay, current reach the maximums and cannot increase. Okay, and then the second one is that if you switch the polarities, okay, instead of trying to push electrons to reach the another side, you switch the polarities, so you try to slow down the electrons. Okay, when you doing that, you see that the current is reducing, right? The current is reducing, which is true. It makes sense because if electron is slowed down, it cannot reach another side, so you have low currents. Okay, so you switch polarities. Okay, the current decrease. Okay, and then at some point the current's gonna be 0, which means that if you apply these currents with the switching of the polarities, there is no electron that can move until it reaches another side. Okay, so in this case you can say that the kinetic energy of the maximum electrons, the Ke max, should be equal to the electrons time the potential difference you are putting there. Okay, subscript S is what we call subscript S is what we call the stopping potential. Okay, stopping potential. Okay, so if you make the bigger potential difference, but in the opposite polarities, for example, you put the minus here, and electron cannot go to the minus side, right? They have the this side gonna try to repel the electron out. So if no electron can reach this one, so it means that the maximum kinetic energy that electron have should equal to this this value. Okay, and then next one is that if you we're looking on the high and the low intensity. So if you increase the intensity increase, the currents also increase. Okay, so this is what we get from the experiments. Okay, there's no explanation yet what happened, but this is what we get. So as a physicist, scientist, or engineer, you need to question that, and you try to do different experiments to study the characteristic of these experiments. Okay, so they are looking on the different way. Okay, first is that the concept is that they try to vary the light frequency and the light intensities. Okay, and what they try to measure is measure the kinetic energy and measure the currents. Okay, and in summary is that if you increase the light frequency, the kinetic energy is increased. It follows. Okay, if you increase the light frequency, the kinetic energies increase. Okay, but if you increase the light intensities, the kinetic energies remain the same. Okay, so this is what we get from here. Okay, then if you increase the light frequency, the currents gonna be the same. If you increase the light frequency, the current I gonna be the same. This is current. Sorry, this is current. This I is intensity. So not too confused. And then if you increase the light intensity, intensities increase. The currents also increase. Okay. So this is this kind of the relation that we have. Then what you need to do is that this experiment has been done in one metal plate. If we change the metal plate, what's gonna happen? Okay, so we change the metal plate to metal 1, 2, and 3. It can be any kind of the materials. And then you do the experiments, and then you try to fit the plots. Okay, it seems to be linear. Okay, Einstein came to the explanation of that. But if we don't have the Einsteins, and you say you see this kind of plot, what you're gonna do? Let's think about this. What you're gonna do if you see this plot? Okay, it's linear plot. And in the lab, if you see the linear plot, what you're gonna do is finding the slope, right? Finding the y-intercept, finding the slope, and that's what you have to do. So you're trying to find the slope. So it's linear, right? So you have the linear equation y equal to the mx plus c, right? Okay. C it's what we call the y-intercept. Okay, m is slope. X in this case is frequency. Y in this case is the kinetic energy max. Okay. So Einstein did that for metal 1, 2, and 3, and he see that the slope it's equal to the h. It's equal to the 6. Sorry, I should not say it's equal to the h. It's equal to the 6.62 times 10 to the minus 34 June 2nd. And he said, yes, this is the slope. And we see this number. It's coming from Planck, right? So this something is relation to the what Planck introduced as the quantize of the energies. Okay. C is the y-intercept, right? So if we say that we would like to do the C, so you can assume that the kinetic energy become 0. So if the kinetic energy becomes 0 at that point, if the kinetic energy becomes 0, you will get C equal to the minus h over frequency, right? Frequency h equal to lambda c. Okay, and we call this thing it's the critical wavelength, for examples. Okay. And then h it's constant, c is constant, so h times c is constant, and it has the value of 1240, I think, electron volt nanometers. Okay. And this is what we call the work function. So it's minimum frequency that you need to put to make the electron out. Okay, so if you put lower frequency than this point, if you put the lower frequency, you will not see any electron out. Okay, so you need to put the frequency higher than this, and you get electron out. Okay. So in 1905, Einstein derived the Planck result, okay, by assuming that the quantization is a fundamental property of light and another electromagnetic radiations. Okay, and this lead to the concept of the photons. Okay, the photons that have the photons have the mass equal to 0, and it has the energy equal to the Pc equal to the hf. Okay, so this is what Einstein has. Okay, so E equal to Pc, this is come from the special relativity, equal to hf, this come from Planck assumptions. Okay. So this is the second experiments and the explanation to that. Today, the photoelectric effect is used in the several tools. For example, this one, the photo multiplier tube. The how it's work is that the photoelectric effect happens, okay, but it can be very weak. But this thing it's multiply the signal, so the name it's a multiplier. Okay, so it enlarge the signal, multiply the signal, so that you can measure that precisely. Okay. So while the developing of the theory, so physics changing from the classical world to the new world that called quantum world. Okay. So there is a conference, Solvay conference organized. The first time it's in 1911 and it's every 3 years by invitation only. So the first time until the fifth, it's organized by by Rowlands. So maybe you remember from the name of the Rowlands transformations. So the topic was announced as the theory of the radiation and quanta, because it's very early time that we start to realize about the quantizations, the energy level. Okay, so if you're looking on this in this picture, so this is Einstein here, Planck it's here. Okay, this is Poincaré, so the one who names the Lorentz transformations. Okay, and this is Rowlands. Okay, and the most famous one is on the fifth conference in 1927 in the topic of the electron and photons. So in that time, Einstein became a very popular, very famous scientist. Okay, so he's now in the front, and this is Planck, and the same, this is the Curie, and this is Rowlands. Okay, so most of these physics is, I think it's from how many, about 10, 12 of people in these figures got the Nobel Prize. Okay. There is another effect. Okay. This effect called observed by Compton. Okay. After Compton observed that the X-ray from the electrons in a carbon target found so he found that the scattered X-ray have a longer wavelength. Okay, so what he did is basically he's shining the, so this is the model, so he's shining the photons. Okay, it hit the electrons. Electron is scattered out from the carbon atoms, and then there is a radiation out scattering photons. Okay, so he found that the frequency is different. So there is a shift here. Okay, so the wavelength is increasing. Okay, so he came to this shift of the wavelength here. Okay, the lambda prime minus lambda 0 equal to the h over mc 1 minus cosine theta. Okay. How to calculate this thing? It's not too difficult, so I can guide you on how to do that, and maybe you can complete it. So you have the you have the photon coming. This is the interaction point. You have electrons scatter with the angle phi, and the photons scatter with the angle theta. Okay. So this is kind of the collision thing. So you can expect the conservation of the energy and the conservation of the momentum, right? The mass energy conservation. This is what you have to think about that. Okay. So before the collisions, you have the energy of the photons, right? It's equal to the HF, okay? And the energy of the electrons, mc squared, because electron is at rest, right? And then for the energy after, you have the energy of the photon, but it's changing the frequency. Electron is moving, so it's mc squared divided by 1 minus v squared over c squared. So we consider the relativistic effect on that, okay? Or if you can say this is HF prime, so this is the total energy, right? So the total energy can also be explained in this formula, p squared plus m squared c4. Okay. So you need to balance this formula. Okay, and you would like to have the difference between the frequency, because if you know frequency, you know the wavelength. Okay, so one thing that you don't know in these two formula is the momentum. So you need to find where the momentums come from. Okay, you need to consider the momentum conservations. Okay. So for the momentum conservations, you consider in the x positions, in the x directions. Okay. So for the photons, maybe I should mention this way. The energy equal to the PC equal to the HF. Okay. So momentum equal to the HF over C or H over lambda. Okay. So for X, you have H over lambda equal to the H over lambda prime cosine theta plus momentum of the electrons, right? Which is P cosine phi. Okay. And then in the y directions, the H over lambda prime sine theta equal to the P cosine, P sine theta. Oh, sorry, P sine phi. Okay. So now you can form P. You can form by finding the P square. Okay. So what you have to do is just basically move this term to this side. Okay. And then you have P square, P cosine theta from this equation and P sine theta from this equation. If you square and then you add it together, cosine phi square plus sine phi square is gonna be equal to 1. Finally, you will get P square. Okay. And then you can place this P back to these equations, and then you're gonna get the relation of the coming from the Compton effect, from what Compton see. Okay, so the lambda prime minus the lambda 0 equal to the H over mc 1 minus cosine theta. Okay, so try to find P square and then put back. to mass energies conservations. Okay. Okay. Then next one. Okay. After Einstein proposed the provide the explanation of the photoelectric effect. Okay. So just okay. Sorry, I have to rearrange my idea. So what I'm gonna say is that following three experiments, three explanation. First, it's about the blackbody radiations, followed by the photoelectric effect and the evidence from Compton scatterings. So this leading to the postulates come by de Broglie. Okay, in 1923, de Broglie postulate that the photon have both wave and particle characteristic. Okay, because we are talking about E equal to PC equal to the HF. So this we're talking about the momentum. So this is particle. This we're talking about the frequency and the wavelength. So this is wave. Okay. So he said that perhaps all form of the matters have both properties. So everything should have the wave property and the particle properties. Okay, and this is in his PhD thesis. So it's quite remarkable that in the PhD thesis that he can propose this one. Okay, so he studied at Sorbonne, so currently it's University of Paris, part of the Paris. Okay, so what he proposed is basically this. Let's check. Let me check what is the form that written. Okay, so he put P. So he say P equal to H over lambda. Okay. So this is what he proposed. So the momentum is the representation of the matter world, and the lambda is represent of the wave. Okay. And this can be considered as the generalized of the Einstein equation, because as I did before, so PC equal to the HF. So basically P equal to the HF over C, and that means it's H over lambda. Okay. Great. So now we have that. But this is the assumption, so we need experiments to describe it. Okay, so the experiments come from Davidson and Kramer. So they work in the Bell Lab. Okay, and their work it's the first time that leads to the first Nobel Prize for the scientists, physicists in Bell Lab. Okay, so they built the apparatus to measure the energy of the electron scattered from the metal surface. Okay, so how the equipment work is that they have the filaments, and these filaments can create the electrons. Okay, and they have the targets, metal targets. So this is nickel, and it scatters with the angle theta, and they have the movable detectors. Okay, detect the I would say the pattern of the after this of the scatterings. Okay, and what they see is that they see something close to what we call the diffracted, which is the diffraction, which is the phenomenon of the wave. Okay, so this is what they get. So when they vary the voltage, okay, and then they're trying to looking at the peak, okay, of the intensity. So larger, it's mean the peak of the intensity, and this is what they get. So it was surprised that they find that the certain angle that was a peak in intensity. So they found a peak, okay, oops, sorry, that at certain angle there was a peak in the intensity of the scattering electron beams. Okay, it should not have a peak. I mean, it should just, I mean, if it's just normal matters, it should just flow things, and you don't really see that at certain angle you see intensity is increased a lot. Okay, and that is the pattern of the diffraction, right? Because in the diffractions you have a peak somewhere. Okay, so, and that peak is correspond to what we understand from Bragg laws. If you remember, Bragg law, we are talking about the layer of the substance, and then do shining it with the X-ray, and it's scatter, right? You see the path difference, and this path difference create the interference patterns. Okay, and in that time, I think you have the equation of the 2D psi theta equal to the n lambda. So this is Bragg. Okay, so from the explanation from de Broglie, so lambda will equal to the h over p. Okay, it's gonna be h. P is equal to the square roots of 2me, right? Because yeah, p square equal to the, right, over 2m, it's the energy. Okay, and E equal to the charge of the electrons, and with accelerations with the voltage of V. Okay, you know E, you know V because you vary that, you know M, so you can find lambda. Okay, so finally lambda can be found as the 0.167 nanometers. This is for the voltage equal to the 54 volt. Okay, this one you see the intensities. But now we consider about the Bragg. So we have n lambda equal to the 2D psi theta, right? So you would like to find lambda, you assume n is equal to 1. You know, you do the experiments by X-ray, you get the D. So the D is 0.092 nanometers. Okay, this is coming from the X-ray diffraction. Okay, then you need to put the angles. Okay, but this is you need to be careful. You cannot put 50 degree here. No. Okay, no. Why? Because in Bragg, I think I mentioned this when we had a lecture, that the theta in Bragg is this angle. Okay, it's not the incident angle as we discussed usually in the light ray or image. Okay, but for the Davidson grammar, so this is the angle. Okay, this is the ray, this is scatter rates. So this is the angle. It's not this one. So if you use the Bragg, you need to talking about this angle, but this is not. Okay, so let's say the light come here, it's go here, and this is what we call theta, and this is theta of the Davidson and grammar, and this is theta of Bragg. Okay, so it's different. So you need to put Bragg here, theta of Bragg. Okay, And what is it? So this is the right angle. Okay, so theta of Bragg, you put it's 90 degree minus theta of the Davidson grammar divided by 2. Okay, so you need to put 50 here. Okay, so 50 divided by 2 is 25. So 90 minus 25 is 65. Okay, so you put 65 degree, you will get lambda equal to the 0.165 nanometers. Okay, and this is more or less identical. Okay, so this is experiment to show that electron can behave as a wave. Okay, it's the first evidence after de Broglie assumptions. Okay, great. So now we have I think we finish the today lectures that we cover the history and introduction of transition from the classical electrodynamic, classical mechanics, now move to the quantum mechanics. Okay, so today we're talking about the evidence from the blackbody radiations, photoelectric effect, Compton scatterings, and the idea coming from Planck, and Einstein used that to describe to explain the photoelectric effect. Okay, and finally, when we have the postulate from Planck that all the matter should have the wave and matter properties, and this is proved by the experiments from Davidson and Germer. Okay, so I think this is all for these videos. So next time we're gonna talking about the using this wave property of the matter to explain about the double slit experiments, and then uncertainties, and then we can move it to the particle in the box problems. Okay, so thank you very much, everyone. See you in the next video. Bye bye.